And so, your slot, so okay. So again, like all of these are worked out in the slide, like whatever we are working together in the class. So your slot is between 0 and m, right? That basically tells that I can actually, during the base decode step, which we now have to work out, I can actually recover the block ID and slot by just taking the modulo operation and the integer part of division, right? And the only thing here we used during decoding was the fact that, oh, my slot is always between 0 and m, and my encoding step was block ID times m plus slot. But okay, we still haven't recovered a symbol or the previous state. We just recovered slot, which was this whole big term, right? Like cumulative of something plus state modulo operation with some frequency. So any idea, once I know the block ID, so now I know the block ID and I know the slot, how can I maybe recover the symbol out of it? So I know the value of my slot, which is also equals to cumulative of S plus this whole thing, X previous modulo frequency S. Here is a hint. We actually know something more about slot, right? Slot is not only greater than equals to 0, less than m, but actually it's always greater than equals to cumulative of S. Sorry, let me just rewrite this. And less than equals to cumulative, less than strictly of cumulative of S plus 1. Right? We just worked out a tighter bound. Does this give you a hint on how you can find the S? Again, like none of these questions are hard. Feel free to throw out whatever the first thing comes in your mind. Like it's okay. Yeah, okay. Anyone wants to build up on that answer?
The first S such that the last S such that cumulative S is less than equal to slot.
Cumulative S is exactly. So basically the point is your cumulus is basically a monotonically increasing array. So what I'm showing here is, let's say this is, actually, no, this is wrong. I need to start from 0. Okay. So your cumulus, right? So this is, let's say, symbol 0, symbol 1, symbol 2. At each point, whenever you encounter that symbol, you are adding the frequency of that symbol, right? And so once you know that, I don't know, slot basically is a number which is always between cumul of something, all you need to find is the band in which the slot lies really, right? So we know that this is an increasing function. All you need to do is like find me the S such that your slot is actually greater than the cumulative of that guy and less than the cumulative of next one. And cumulative actually is a sorted array. So this is where your computer science search information would also come into play. You can do this very efficiently. But basically the step which you use is, so again, you use this hint that your cumulus between this, and all you can do is do a binary search, right? All you need to do is like do a left bias binary search to find the symbol S, which is such that cumulus is just less than the slot. And then cumulus plus 1 is greater than that slot. And because of this exact property which we worked out, this is going to be unique. There's only going to be one symbol which is going to return that. Are people with me? All right. So are we done? So now we know how to decode the symbol. Should we call it a day? We need to know the previous state, right? Like as we know, this is a symbol by symbol operation. We recovered our S, but we also need to uniquely determine what our previous state was. Any ideas? So now by this point, by step 2, we know what our S is. We know what our S is. We know the block ID, which is X previous integer division of frequency S. And we also know our slot, which is cumulative of S plus this, I'm not gonna rewrite this, but you know the modulus term this point. So can we work out the X previous? Or do we need to do something more? Mm-hmm.
The remainder is in our slot. We just subtract cumulative S to get that remainder part to get the whole X previous.
Exactly. I'm not gonna repeat. I'm gonna actually, this is where I'm just gonna give you the answer. It's basically direct manipulation of terms at this point. All you need to do is rearrange your original term, right? So remember your encoding was X equals to X previous by frequency S plus cumulus plus X previous mod frequency S, right? You know this term. You know this term because you have figured out the symbol S. So you know exactly what cumul S is. So at this point, you know the value of X previous modulus frequency S, and you know the value of X previous integer division of frequency S. So you can just rearrange the terms to figure out what your X previous was. And this is what it turns out to be. So just at this point, you're just rearranging the term and using the fact that, oh, you know the S, you know the exact value of cumulus, and you're just using the initial equation to get back X previous. So great. So ideally this should, like, while we were working it out, it seems that it should work out, right? Like in the sense, like we should just, we are just reversing the steps, very similar to how we were doing in the symmetric numeral systems. We are just reversing the steps and recovering symbols in opposite order and recovering the state, right? But let's work out an example together just so that, I feel confident that you guys understand, even though it's just redoing the same maths operation. Personally, I feel just redoing these algorithms by hand give me a lot of intuitions on like what's happening, even for maybe simpler examples. So yeah, I encourage you guys to do that. So remember, like in our previous case, we worked out the X final was this, corresponding to some bit array. So it's like the same running example we are working with, where I have 3 symbols ABC, with probability 3 by 8, 3 by 8, and 2 by 8, and the cumulative frequencies for them is 0, 3, 6. Okay, and your X final is 101. So let's try to work it out. Let's just do maybe one step together, and then I'll encourage you guys to go home and do the rest of them. Okay, so step 1. So X final is 101. So again, we'll just repeat the steps here. Step 1, step 2, step 3, like the 3 steps we worked out together, right? Okay. So step 1 is getting the block ID and slot. So your block ID and slot would just be division by 8, right? Because my M is 8. And let's see. So Can somebody check that your block ID would be 12 and slot will be 5? 88, 96. Yeah, seems about right. Okay. So this is step 1. Now step 2 says find the symbol S such that my slot is in between the cumul of the previous one and the next one. Right? So our cumul S array is this. 5 belongs in between 3 and 6. And so my symbol would be this guy, right? The second one. So my symbol is 1. Okay. And that also means my cumul S in this case is just 3, which is just the cumulative probability of 1. And then the step 3 is just working out this maths. So let's just do it. X previous is block ID, which is 12 times frequency of S, 3 plus slot, what's our slot? 5 minus cumul S 3. So this gives 38. So the algorithm outputs, so let me maybe write it. Right. So you return the symbol and previous state. So your symbol return would be, symbol is 1 and your previous state is 38. Okay. So now let's just, okay. We can continue doing this, and I encourage you guys to go home and continue doing this. But just as a reminder, let's see where we did the encoding. Okay. So this is where we did the encoding, right? We just worked out the first step going back from 101, and the symbol we outputted was 1. And the previous state we outputted was 38. Okay. So you see, it's like the exact backtracking. So the basic idea is as you keep adding symbols, your state is increasing. And when you start decoding, you start decreasing your state and outputting back the same symbol at each point. This was like 1, 0, 1, 0, 2, 1. And then while coming back, you'll just output them in reverse order. Okay, so here I just did only one step, but please go home, work out this example, and ideally you should be able to recover all the previous steps. Any questions? Mm-hmm.
So is this asymmetric? I always said it was symmetric earlier because they're inverses, but isn't it still, are the encoded key process still going through the exact same states?
So asymmetric was not for that. It was because of numeral systems, right? So symmetric numeral system is no matter what point you get, you're multiplying it by 10. In our case, the thing which you are multiplying the previous state with is very different, right? It depends on the symbol which is coming in. So if you were encoding 0 to 10 with very different probabilities, we'll be multiplying each number by a very different amount. So that's kind of the asymmetricity part of it. But actually this is a very important point which you brought out. You need to ensure that as you are going forward and backward, you reproduce the exact same state, because that's the real point which is ensuring the losslessness. Okay, and so this is just, I've already opened it. This is just a link. So, Kedar, whose name we hear a lot because he co-designed the course with us, had passed, he had written this blog post on ANS. And this is just an interactive. So if you just want to play with some symbol counts, input string, see how the state kind of expands, you can just go and play with this kind of thing. So I guess in our case it was, I forgot. 1 second. Let's just check it. Was 0, 1, 0, 2. Can somebody remind me quickly? What was the input string? Oh yeah, 1021, thanks. So let's just put in 1021, comma 0, comma 2, comma 1, and try it. And you see like we recover the states which we were seeing. And you can play with different symbols, different frequency length. Would encourage you guys to still work by hand so that, but you can use this code snippet interactive to see if you are working out things right or not. And then when you decode it, you start with some state. So in our case, wow, is this not opening up? Interesting. For some reason, it's not allowing me to edit it. But okay, the point is you can change the state here. I think I'm on iPad, so it's not allowing me, and you can input the number of encoded symbols. And again, like the output which you'll start getting is the states in reverse order and bits thrown out in reverse order. Yeah, so this is just a tool which you guys can play with. The link is in the slides. Let's see. Okay, so this is now just combination of everything which we have learned so far. So just to summarize it one last time, the encoder works like this. So you start with some initial state. For each symbol in the data input, you run some base encode step which takes in state and symbol and gives you updated state. Okay, and then the final output of the encoder is this 2 binary. Which just converts it into a binary. And the base encode step does this block ID times m plus slot. Okay. And then this is like the combined decoder. And so at this point, this is called range ANS encoder and decoder. These are the operations. So during decoding, you just do the exact inverse, right? So you convert bits to final state first. Then for the range in symbols, you run the base encode step. Your base encode step has to return the symbol and the previous state. And we just talked about how we can recover that. And finally, you need to return the reverse. This is important. You are always decoding in the reverse order. Okay. So now, if you think about like, so how we motivated RANS, right? Like the first question which I asked you when we moved from symmetric numeral systems to asymmetric numeral systems is what's happening with the state, right? So again, with same argument, your state now is increasing by approximately 1 over probability of your symbol S as your states keep increasing. And so the final state can be represented using approximately log 2 of X final bits. Correct? And so the question for you guys is, what's the approximate encode length for an input SN? So now suppose you have a stream of symbols S1, S2, Sn, which was like 1021 before. What's like the encode length? Approximately.
It would basically be the expected value of log 2 of 1 over ES, which is just entropy.
Exactly, right? So now, basically for each symbol, as you were encoding Sn, even without block lengths, so as to say involved, like we were seeing in Huffman code, you are basically multiplying it. Let me write it with this. Yeah, you are multiplying first symbol. When first symbol comes, you are multiplying X by 1 by PS1. Second symbol comes, you are multiplying it by PS2, roughly given S1, so on and so forth. And so finally, like the rough length which you will get is you are multiplying the whole symbol by 1 over probability of the n tuple of whatever that symbol is. And so your length is just log inverse of this. And again, tying back to a thumb rule, this basically tells us, oh, we have suddenly found a very good encoder decoder because it gives you something very close to entropy. And so we are not talking about like, so this is all a very hand wavy argument, I know, but this is more like, I guess, in the spirit of the course. For those of you who are like mathematically enthusiastic about how to get like very formal bounds for ANS, like we have been doing for arithmetic coding, where we saw that there was a 2-bit overhead over whatever the block length of your symbol was, or in the case of Huffman where it was 1. We can discuss it offline, but it's not trivial to analyze. What I really want you guys to take away from this whole discussion is that intuitively it makes sense that this compressor is somewhat optimal. It can give you good compression rates like arithmetic coding was giving. This was roughly the hand-wavy argument even in the case of arithmetic coding, right? Okay. And something very interesting actually, which just to connect it to what you guys will see in future is, so I think when I first saw it, for most of the people I know, when they first saw RANS, they had probably the same reaction as some of you, like, where did that equation come from? Like, why does that cumulus plus mod, blah, blah, and then you somehow beautifully come up with decoding mechanism where everything works out. You just had those somehow some bonds which kind of solve everything, right? In this discussion we went over, I continuously gave you hints, but now imagine you just somehow surprisingly came up with that one day to a friend and say this works. And historically that's somewhat how it happened. Somebody, Yarek Duda actually, who's amazing, he came up with this approach and it took people a lot of time to really understand like what's really happening. But one actually very cute, I would say, way to connect back to what's really happening is this idea of bits back coding. And we'll not discuss it right now. It's just something I want you guys to kind of just know about. So this is like another way to think about RANS. So we took one approach, but you could have taken a completely different approach and would have basically landed at very similar looking equations. And it basically has connection with this joint entropy formula. So if you were to compress X ideally, one way to think about this joint entropy formula. So this is for any other random variable Z. This is just an identity. This is a mathematical fact. You can think of encoding and decoding X as like doing something with joint distribution of X and Z, and then doing something with the conditional distribution of Z and X. Okay. And I know it's not making sense right now, but basically this minus sign, right? So you can encode a symbol X using some encoder decoder pair 1 and some encoder decoder pair 2, where you have some minus sign, which we haven't really dealt with, right? Like everywhere we have been dealing with positive lens, positive everything. This kind of gives the name bits back. Just like you'll encode something, but then you'll also give some bits back to remain like close to very ideal thing. And it's always might sound mysterious, but go check out homework to Q4, hopefully soon, less than 24 hours. You should be able to see it, work it out. And then for those of you who were a bit, didn't appreciate the fact, like what does it mean to have a conditional entropy, deeply? Well, like next few lectures, as Shubham I think pointed out even in the next class, it's going to be like, now we are going to be talking about conditional entropy, conditional probability distributions, because we'll stop assuming independence. So basically next few lectures and working through homework will really make you understand whatever we did today from another light independently. And okay, so at this point I want to go into some qualitative aspects instead of everything. So some properties of RANS, like now where does RANS stand, right, with respect to arithmetic coding? So first of all, we understood that the performance is optimal and actually very similar to arithmetic coding. Goes back to our rule of thumb, which we just talked about. We are actually doing reverse decoding. This can be a lot of problem for streaming algorithms if you think about it. That's why I've been highlighting like reverse decoding, right? Because it's no more like the encoding is in streaming fashion, let's say, but decoding now will give you symbols in opposite direction, which might not be good if a low latency or a high throughput encoder decoder pair is your demand. But you can see there are schemes to work around it. And it actually has simpler encoding and decoding. So this is something which we didn't really talk about. But Shubham mentioned last class, like arithmetic coding is amazing, but it has these floating point operations involved everywhere. Whereas in our encoder, I'm just going back to our RNS encoder, actually you have some operations which can be done very efficiently. So for example, even though you have integer division, you can pre-compute 1 over frequency s. So you don't, like, this is just like, this can be cached and done once. Similarly, like, you can just be intelligent about the choice of m. So if m is a power of 2, multiplying by it is just a left shift, which can be done extremely efficiently in hardware. So basically, choosing engineering choices gives you a lot of efficiency in terms of how RANS can be implemented, and is the reason why it has fast encoding decoding faster. Okay. But there is actually one issue which we still haven't solved. So RNS sounds great. Like, any guesses practically what might be one of the issues? Yeah. Yeah, so that's probably a comment which is coming after attempting homework 1. Yes, you do have to find m, which works well. But I would say that isn't fundamental issue. Can be worked out. Take m large enough for, like, probabilities are never exact. Let's say for whatever precision you are working with, maybe it's okay. But there's actually the fundamental issue. So if you look at, like, the input symbol string, as it keeps growing, your state just never stops increasing, right? Like, you're always increasing your state. You're always multiplying it with something. And so no matter what you do, after a few symbols, when I say few, maybe around 20 to 40, you'll already reach a state which will start overflowing, no matter what you do. And this is, like, I would say this has a parallel to, okay. Yeah, so this has a parallel to what we learned in arithmetic coding also, right? Like, so as you keep multiplying probability, your intervals keep becoming small and small. And a lot of practical compressor goes into a lot of depth into solving these issues, because these are very important and practical issues. And so, yeah, basically after 30, 40 symbols, you'll go above. Okay, so one solution to avoid this is, like, you can restrict the x to be an interval L, h. One thing which you wouldn't want to do is, like, restart, right? You wouldn't want to be like, okay, whenever it overflows, I reset my state and I start from the beginning, because that's losing all the advantage. It's losing the block advantage. It's losing the fact that states need to be high enough to actually get you a compression ratio near the log probability, right? Log 1 over probability. And so one way to solve this is, so we'll not I don't want to get into the details given the time, but basically now you will try to keep the state in between this interval L, h. And one way to do this is, when you do the encode step, your first step is, like, even your base encode step always assumes the state which you are getting is in between L and H. So before actually calling this step, you need to call a shrink state step, which takes some x and returns the state x shrunk, which is in between some predefined window, L, h. But obviously this step will be lossy if you don't actually give out some bits with it, right? Like, because you're changing the state, you're just dividing it and putting it to some other thing, you are losing some information. So this step also gives out some bits. And yeah, let's not go into the details. Let me just show you, like, how this kind of function looks like. So if you start with x previous, something like 22 or 1011b, one way to get this shrink state is to always divide this by 2 and output the last bit. So for example, if you start with 10110, at first step, you can do 1, 0, 1, 1, and then you can out the last bit 0. Next step, you can output 1. You can take out 1 and add it to the list of out bits and keep it to 1, 0, 1. And you keep doing this till your state basically comes in the interval L, H. Yeah. And this is basically your string state function, which is while your base encode step is not in this interval, you just maintain an out bits, which is just modulo base 2, and you keep shrinking your original range. Okay. So what it's doing is that at each step, I might output some bits. I'm not really waiting to encode the whole state towards the end. And at that point, I output some bit. That's really the key difference. And then a really important question to think about is how many bits do you have to stream out, right? What is this L, H? And in practice, like, you need to ensure two things, right? Whenever you are shrinking this state, you need to ensure that there is uniqueness involved. There is only one. There is one, first of all, and only one symbol, which is going to lie, given no matter what state you started with, to get it in between this L, H window. Huh? And don't worry about it. That basically gives you some bound about what your L, H can be. And this was like what was chosen in the original paper of ANS. And choosing something like this satisfies these conditions. And I'm not going to cover it in class, I think, in the interest of time. I don't want to go over. But all of these are also present in the notes. So I would encourage you guys to read the notes to understand like the basic idea, which we just discussed. But you might imagine one thing which I'll say, since we have almost discussed the idea, like, so, come on. Okay. So the full decoder now, so will involve some expanding of state, right? Because right now you are shrinking some state. So when you are decoding, you need to somehow expand that state to get back the original thing. And that will use the out bits which were involved. So you'll have some X shrunk, some encoded bit array, and a reverse operation of whatever we saw, right? And so your decode step it's going to be exact opposite, same spirit. So your first step would be base decode step, which will give you some state and shrunk state, and then you'll expand that state, which is going to do a reverse operation. And combining these two basically gives you a full streaming encoder and decoder. Okay, this is like the complete thing. Couple of things which happens in practice again is like you'll take m to be power of 2. You'll choose t to be as large as possible. When streaming out these bits, you might not want to do a single bit at a time, but bytes at a time. Okay, and we have so in SCL, we have the RNS implemented. And again, like all the previous lectures, I would encourage you guys to like go over the code, see if you understand it. Yeah. And we didn't really go over TANS in this lecture, but that's really like the basic idea in TANS is how can we speed this up? So the name of TANS is table ANS, right? And so the question really is, what else can we cache? How can we really speed this RANS up? Any ideas given homework 1, what we have seen so far? How do you, like, what do you cache? How do you cache things? Like one recurring theme, which is, which we have seen maybe even in tree-based codes, is trees are slow because you have to take decisions, right? And so whenever you have to speed up something, you might want to come up with some lookup tables. That's like a very, very good rule of thumb in when you're coding. If you can come up with some lookup tables, you can really speeden up your code. And that's basically the idea of like caching RANS and TANS. And it kind of relies on the fact that like in our RANS base encode step, when you go from this state symbol to a new state, you are always maintaining it between the same lower and higher window. So you can basically pre-compute, given whatever your previous state is going to be, whatever new alphabet is going to be, what your new state ever can be. And so you actually never even have to compute that. And that's called TANS, and it basically takes some hit in terms of performance, but the key idea really is that like lookup tables are really fast, so use them for speed trade-offs. And so kind of this is the last slide, but this was also the first slide where we started from. So again, combining like all the ideas which we learned. So I hope now you guys understand exactly how RANS works. TANS, we didn't go in details, but like we have some notes. You are welcome to go through the notes. You are welcome to go through the code in SCL and come talk to us if you want to understand that better. Variants of RANS and TANS could also be interesting project proposals and ideas to be implemented for practical compressors. These have really replaced arithmetic and Huffman coding in almost many new modern compressors which have come out. And the things to again notice is that like the compression performance of RANS is very similar to TANS, and that's because of that rule of thumb, which we have been looking into and which we were able to achieve with RANS. TANS takes some hit because we cache and we don't do exact operations. But on the other hand, if you look at speed, TANS has speeds which are very, like at least decode speeds which are very close to Huffman, and then encode which is competitive at the very least. Right? And yeah, this was, I would say, the last lecture in the series of where we started, like if we look back, we started this class with like very simple examples, IID. We worked out how you can encode them to how you can encode them optimally, like how you can encode them losslessly to how you can encode them optimally losslessly. And then we learned various different practical lossless codecs. Really like various different approaches. Huffman coding, Shannon coding, Huffman, I repeated that. Arithmetic coding, ANS, right? But so far, we really had a strong assumption, like we are talking about entropy, but everywhere we assume that the symbols were IID. But in real life, like you can have symbols which are highly correlated. The next symbol might not be independent of the previous one. Right? Take anything, take language, right? Like the symbols are highly correlated. And the next few lectures will go into the details of how do you actually work with real data which you see? How do you deal with this correlation while ensuring lossless compression performance? And how do you do it adaptively? How do you like, okay, some teaser trailer, how do you use things like LLMs to get your state-of-the-art compressor? So I think we're gonna change the direction a little bit, but whatever we have been studying is gonna keep building on that. Yeah, thank you.